As a part of this chapter of this course, that is advanced spectroscopic technique, today I am going to discuss about photoluminescence spectroscopy. Photoluminescence obviously means light, and luminescence means something which shows lights. So, therefore, it is a day to day affair, but today we are going to discuss about the basic concepts and then how it is to be utilized. So, the way I am going to schedule this lecture, put this lecture into perspective is by this way. First, I am talking about the principles of photoluminescence, then something about quantum yield and lifetime, and then I will go to fluorescence spectroscopy, some instrumentation and experimental procedure of fluorescence. Fluorescence has become a major spectroscopic technique as a part of the photoluminescence. So, therefore, that needs to be discussed. In fact, let me tell you also the fluorescence microscopic technique has also come into picture nowadays, especially for the biological specimens, where some of the important parts of the body cells of the different animals can be tagged with the dyes and then can be imaged using photoluminescence or fluorescence spectroscopy. Well, what is luminescence by this way? Luminescence is basically a phenomenon where a light is emitted by a certain substance, and that substance appears to glow actually. As you know, nothing actually emits light by per se, which when you see some object, because the light is reflected from that object. Obviously, there are exceptions like sun or stars of the in the sky, so that they emit light, but I am talking about the objects in the on the earth. So, exceptional objects which can emit light, and then by emitting light it glows, basically known to be photoluminescent, and this whole process is known as luminescence. It occurs mainly because of the electronic transitions. Like an electron, if it is excited from the ground state, shown here, electron excited from the ground state to the excited state by certain energy. You can either talk about any kind of energy, either the photo energy or chemical energy or sound energy, and then once it returns from excited states to the ground state, it loses the excess energy, and this excess energy comes in terms of light, and that is why the photoluminescence actually happens. So, luminescence techniques actually based on the measurements of this emitted light, emitted radiations, and as you know, as we have discussed over the last few lectures on different aspects of UV visible spectroscopy or maybe FTIR, the infrared spectroscopy, this emitted radiation is always characteristics of the molecule because of the specific electronic transitions which takes place in such a process. Well, there will be obviously, after knowing the photoluminescence, there will be obviously different modes of excitations. That means, you can excite the molecule or electrons basically from ground state to higher energy state or excited states by different ways. That means, first one is known to be photoluminescence, which is the subject matter of this class today. Excited molecules are results of photon absorptions, like absorption of radiations. So, one certain radiation falls on a molecule, if the molecule can absorb this radiation in terms of the photon, and then we call them photoluminescence. So, there are two kinds of phenomena that also can occur. One is fluorescence, other is phosphorescence, which we will discuss separately after certain slides. And then you can also have chemoluminescence or chemiluminescence, that is excited molecules can be because of results of chemical reaction. Certain chemical reaction can also lead to excitation of molecules, where electrons can jump from ground state to excited states. Then heat can also be used for excitations, which are called thermal excitations. So, that means there are three modes of excitation. One is by photon absorption, second one is by chemical reaction, and third one is known as the thermal excitations. Well, before going into details of many of these transitions, electronic transitions, let us talk about some definitions, because this will help us in understanding the whole process. Photoluminescence is, as I have told, is an absorption of radiant energy and re-emissions of the some of the energy in the form of light. It can be fluorescence or molecular phosphorescence process where molecule emits the absorbed light. The light emitted is almost of longer wavelengths than the absorbed, obviously, because the amount of light energy emitted will be always less than the amount of energy absorbed. Some amount of energy will be spent on some other processes. And normally the light is emitted with a time delay of about 10 to the minus 8 seconds, that means close to 10 nanoseconds. It is a very, very small time scale I am talking about it. In that case, this phenomenon is known as phosphorescence. So, you understand now that if the light emitted with a time delay of 10 to the minus 8 seconds, that is 10 nanoseconds, we call this one phenomenon to be phosphorescence. But if the light emission occurs approximately equal to the less than about 10 to the power minus 8 seconds after the absorption of photon is called fluorescence. So, this basically difference between the phosphorescence and fluorescence in terms of time scale. So, in case of fluorescence, time given or actually delay for emission of the light after absorption of photon has happened is less than 10 to the minus 8 seconds. That means, it will be of the order of 1 to 10 or even less than 1 nanoseconds. And in case of phosphorescence, it is approximately tens of nanoseconds. So, this is the main difference between the phosphorescence and the fluorescence. To give you some basic pictures how the fluorescence and phosphorescence happens, first let me talk about fluorescence. As I told in the beginning of the class, the fluorescence concept has been utilized for fluorescent microscopy. In IIT Kanpur itself, in our own lab, we have fluorescent microscope, and then we can use these microscopes for imaging certain species in the cell, living cell or dead cell. Living cell is the best one. So, in this case, I am showing you some pictures taken from cells, and these are actually human osteoblast cells grown on different composites like hydroxyapatite titanium composites, and by using Alexa Fluor 488 dye, we can actually tag this dye on mitochondrion of the cell, living cell. So, therefore, this dye, when it comes in when we put it on the microscope and we use a photon light, can fluoresce. That means, it can emit light in the range of that blue color light you can see here. When you can see each molecule, each cell has a blue color light emitting. That means, these cells are live and their mitochondria are working. So, by this way we can probe the cell growth on the material. This is a very widely used technology. So, but it uses the concept of fluorescence. So, that means there are many such dyes in fact which can be used to study or can be used to tag different kinds of the parts of the cell and then study their behavior when exposed to certain kind of external stimuli. Sorry, these are all sarcoma cells, SOS2, they are all cultured for 72 hours, they are not human osteoblasts, they are all sarcoma cells. Okay. So, this is how this can be done. Fluorescence, again taken from my lab, or rather we are talking about phosphorescence. As you know, zinc sulfide is basically used as phosphorus screen. Those of you who have seen microscope, transmission electron microscope or older generation scanning electron microscopes, the electrons after interacting the sample falls on a phosphorus screen actually. And when that means the electrons are like photons, when they fall on this phosphorus screen, they excite certain kind of phenomenon, electronic transitions, and once these electrons come from the ground state, they emit radiations. What is shown here is aluminum oxide and zinc sulfate, ZNS, and on a petri dish kept in a dark room and then imaged. What you see is that aluminum oxide does not phosphorus, but zinc sulfide shows phosphorescence. So, these two things are well known and you have seen, probably observed in the actual life, many minerals are present in this world which actually gives photoluminescence behavior. So again, to give you or strengthen my lecture, or to give you better perspectives, fluorescence occurs when excited molecule decays slowly, but original transition does not include changing electron spin, and this is a relatively rapid process. And however, fluorescence is non-resonance due to Stokes shift, which we will discuss, as emitted energy is less than the excitation energy always, due to the energy level transition that occur before the transition emission. Phosphorescence occurs when the excited electrophosphorence, or when excited electron undergoes a change in spin. So, we will see what is the change in spin. Longer process, longer wavelengths of excitation usually endures for an easily detectable length of time up to 10 seconds. Chemiluminescence, which we will not discuss in detail, but to give you an idea, chemiluminescence is a process in which luminescence and emission of light from a molecule is caused by chemical reactions, that is light sticks. Many chemical actually shows light sticks, and they are much more sensitive than the UV visible spectroscopy. There are many features, attractive features of fluometry, both fluorescence and phosphorescence. They are very inherently sensitive, that is, we can actually detect amount of chemical presence of the less than ppm, parts per million, less than 1.1 ppm actually. They are very selective for the particular chemical presence because the excitation is different, and less widely applicable than absorption methods because limited number of chemical system can be made to fluorescence. That is the major problem in fluorescence spectroscopy, because you need to have a dye, specific dye for fluorescence to happen, and selection of the dye makes the life difficult. That is why fluorescence spectroscopy or photoluminescence spectroscopy is not widely used by many experimentalists. Well, now let us go to the detail of the principles after giving you some idea and definitions. As I said, transitions, there can be two kinds of states in the electron spin. One is single state and the triplet state. In the ground state, two electrons are present per orbital, we know that, and they have opposite spin and they are paired. That means if I have one, suppose p electron level, we have opposite spin of electron, 6 electrons are present, we know that. This is p. S, we have 2 electrons, so 1 up, 1 down, and D have 10 electrons, so 5 up, 5 down. That is what I am talking about it. Now, what happens to singlet excited state? Electron in the higher energy orbital has the opposite spin orientation related to the electrons at the low energy orbital. That is what is shown. So, if I have this state and then excite it, so electron in the high energy orbital has this spin which is shown here, electron in the low energy orbital have this spin, they have opposite spins. That is what is called singlet excited states, and this has certain energy difference that comes as a light. So, in a triplet state, excited state, it is little bit different. What happens in triplet excited state is like this: excited valence electrons may spontaneously reverse the spin, and this process is called intersystem crossing. What is it? So, you have this state, now excitation happens and this electron remains same spin state, but the bottom one can change its spin state, or you can have there can be spin flip, and this is what is called intersystem crossing on IC in the literature. This is always known as IC in the short form. So, electron in the both orbital have now same spin orientations. So, therefore, in triplets excited state, electrons in the both high energy and low energy orbital has same spin orientations. On the other hand, singlet states has different orientations. So, you must remember this. Well, now how to explain this fluorescence phosphorescence behavior in terms of energy level diagrams. Jablonski long back, thanks to him, has actually developed such a kind of diagram to explain this. So, let us suppose S0 is the electronic ground state and S1, S2 and S3 and above up to Sn are the excited vibrational states. I have not shown rotational states, I specifically removed it. So, now if I excite it an electron, that is what is called photon absorption A, it will give you a certain photon, it absorbs it and goes to the S2 states. From S2 states, there can different situations can happen when the electrons comes back to the electronic ground state. First one, what is known as interchange states, which I have showed you, that is the triplet transitions. It can come from S2 to S1, okay, that by this is called IC, okay, and this is called internal conversion, as I told you in the last slide. And then when it comes back from this S1 to the S0, it emits certain light, that is what is called fluorescence. So, as you can understand, initially the electron excited from S0 to S2, and then it loses certain energy by internal conversion, then the rest of the energy which is available is converted into light. So, there is energy loss. Wavelength of the radiation which is coming out because of fluorescence will be smaller, so it will be smaller actually than the, or higher actually than the initial wavelength. Fine. So, that is because energy is less. Now, also what can happen instead of fluorescence, what can happen is that you can have intersystem crossing here from S1, you can have intersystem crossing. That is what I showed you, intersystem crossing here. This is what is intersystem crossing. The spin states can flip when the electron even come to excited states. So, if you have this interstate crossing, then again it comes to a state called T2. T2 is in between S0 and S1, a transition state, okay, sorry, triplet states you can say. And then this from T2 to T1 you can also have internal conversion, that is possible, and then when it comes back from T1 to S0, what happens actually called phosphorescence. So, phosphorescence actually much more complex phenomenon than the fluorescence, and you know, that is why fluorescence is more widely used than the phosphorescence, because there are so many processes involved, explaining the experimental results becomes difficult. Okay, so that is actually how the Jablonski's diagrams are made and discussed. These are all very advanced level course, so therefore you need to understand. I hope you have already got an idea about the energy level energy diagrams, and then you will be able to appreciate this. Well, not only this transition, but also one needs to know about the population of energy levels in the fluorescence process. Population means how many electrons are present in a certain energy level. At room temperature, that is about 300 K, and for any typical electronic and vibrational energy level, one can calculate the ratio of the molecules in the upper and the lower states, that is S2, S3, S1 and S0 is the lower states. Using this formula, this is very simple formula, n upper by n lower is basically equal to exponential minus En by kT, where En is the separation energy level, K is Boltzmann's constant is equal to 1.3 × 10⁻23 joule per Kelvin, and T is the temperature. So, important aspect you have to remember is that it depends not only the energy separation level, but also the temperature. So, if you heat a material, the temperature will increase. So, therefore, this factor will reduce, therefore, the n upper and n lower ratio will increase. So, that is why in many cases we heat a material to get fluorescence. More detailed analysis on this, what is excitation and what is emission for fluorescence. As I said, we will discuss more detail about fluorescence. At room temperature, everything starts obviously at the lowest vibrational energy level or ground states, S0. And suppose illuminate certain molecules, anything, it can be benzene, it can be even organic or non-organic molecule also, with a light of reasonable frequency. And then what will happen? Light will be absorbed, and we can actually apply Lambert's BR law, as we have seen, A equal to epsilon Cl, or sorry, B Cl or Bl, whatever, because epsilon is the molar absorption coefficient, B is the optical distance, and L is the excitation. Okay. So, therefore, its magnitude reflects probability of absorption and wavelength dependence corresponds to the absorption spectrums. So, that is how we can explain the absorption. Excitation actually happens following the absorption. A chemosphere, or is basically basic unit of a molecule, excited to higher vibrational states from the S0 to S1 here, sorry, and absorption process takes place on a much smaller time scale. It says it can happen actually in the -15, that is even lower than picosecond time, and vibration is much slower than actually excitation is faster than vibrations, So, vertical transition principle, which is I am not going to discuss, Frank Cotton principle can also be utilized to explain such a kind of stuff. You can also have something called non-radiative relaxation, that is very easily possible. So, in the excited state, electron is promoted, or it can be promoted to an anti-bonding orbital. Remember all these things we discussed for the UV visible spectroscopy, anti-bonding orbital, pi star or n star, anti-bonding orbital, bonding and anti-bonding. Anti-bonding orbital probability of occupation is very low for the electrons. So, in excited electron can be promoted to anti-bonding orbitals, and atoms in the bonds are less tightly held then. So, that lead to shift to the right of S1 potential curve, shift to the right to the S1 potential curve. So, this is energy. So, it is leading to shift to the right of the excited potential, this is S1 and this is S0. Okay. And electron is promoted to the higher vibration level S1 state than the vibration level that was in the ground state. This is what is called the after excitation. Now, vibrational deactivation or non-radiative relaxation can take place through intermolecular collision at the time scale even much faster than the nanosecond at 10 to minus 12 second, which is faster than fluorescence process, and that is what is called non-relaxive. Here it can actually collision can take place intermolecular, and it can come from high energy state to the low energy states. That is what I am saying. So, that is what is shown here. As you can clearly see, this transition can be related to some extent to this. Well, so once it is the electron has, because of intermolecular collision, has come from high energy to the within this S1, it can come from high energy to the or the lower vibrational states. These are all different vibrational states. Then it can relax from the lowest vibrational energy states to the excited state to the vibrational energy level of the ground states in many different ways. Okay, because in ground state also there are many vibrational energy states available. So, electron can jump from one to any of these, from the lowest this level to the lowest vibrational energy level of the excited state to the S0, that is the ground state energy levels, by different ways, and these relaxations occurs faster than the time scale of the molecular vibrations, and these are all known as vertical transitions in the literature. Energy of the emitted photon is obviously all lower than the incident, because there is some amount of energy lost in the process. Well, as I told about Stokes tips, let me talk about Stokes tips now. Fluorescence light is red shifted always, that is, it comes at a longer wavelength than the excitation lights. This is what is known as Stokes shifts. Okay, when something is red shifted, that means whatever is coming out has a longer wavelength, lesser energy than whatever is given as input. This is mainly because of the forget about this, mainly because of the internal conversions that takes place. Solvent effects and the excited state reaction can also affect the Stokes shifts. Well, there are many other things that are possible, which you may be interested to know. You can also have invariance of the emission wavelengths with excitation wavelengths. It can be invariable, this may not be variable. So, maybe the wavelengths only depends on the relaxation back to the lowest vibration level of S1. Okay, this is what I am talking about it. So, it comes back to the lowest vibration level of the S1. For a molecule, the same fluorescent emission wavelength is observed irrespective of the excitation wavelengths. So, what is that means the fluorescence wavelengths will not change at all depending on the excitation wavelengths. Once it is excited, it has gone to the highest vibrational state of the S1, and then the rest of the process takes place. So, therefore, it does not matter what is the wavelengths of this emission, once it is gone there, it can be fluorescent. So, that is what is called invariance. Well, now comes another very important aspect of fluorescence spectroscopy, that is mirror image rule. So, these are all S0 and S1. Now, I am going to give you a much better picture, and there are different vibrational states V0, 1, 2, 3, 4, 5 for the S0, V prime 0 to 5 and for the S1, and as you see excitations and relaxation processes. So, this is internal conversion and then relaxations. So, that is fluorescence therefore. Now, what is the mirror image rule? Vibrational levels in the excited state and ground states are similar. This is the ground state, this is the excited states, S1 is excited state, S0 is ground state. So, vibration levels are similar. Absorption spectrum reflects the vibrational levels of the electronically excited states. Obviously, this all has absorbed. So, therefore, if I measure the absorption spectrum, I will get all these excitations measured. If I get the relative intensity versus wave number plot, so I will get absorption spectra like this. It will be showing me this. Then emission spectrum, which is coming after relaxations, reflect the vibration level of the electronic ground states, as you see here. So, fluorescent emission spectrum is basically mirror image of the absorption spectrum. So, whatever is coming down, you will be able to see this, exactly this. That is understandable, because one is getting absorbed and the internal conversion, then it is coming up. So, although energy levels will be different, wave numbers will be coming different for the emission and the absorption, but if you put a mirror here, you will see the image. That is also clear from the energy level diagram. Now, let us look into even much complicated aspects of this. What is internal conversion? How does it affect the fluorescent emissions? As the electronic energy increases, energy level grow more closely packed. That is, as this is ground states, these are the vibration levels. This is at S0, that is 10 up to 5, S1, S2. There are two excited states are shown here. Otherwise, I cannot show the internal conversions. Now, as I said, as the electronic energy increases, energy level grow more closely. That is this way. As you can see here, they are getting close. It is likely, most likely that there will be overlap between the higher vibrational energy levels at S-1 and S1, that is, these two are the S1 and S2 are the excited states. So, there may be overlap of the energy levels, vibrational energy levels between S1 and S2 is possible, and these overlaps make the transition between the states highly probable. That is, the transition from these to these states highly possible. Internal conversion is nothing but a transition occurring between the states of the same multiplicity. Okay, same multiplicity means there are 5 multiple states here, 5 multiple states here, S1 and S2 both. So, between these two states, transition can happen at a time scale which is much larger, the fluorescence time scale, that is 10 to the minus 12, that is picosecond, and energy gap between S0 and S1 or S1 and S2 is significantly larger obviously than the adjacent state between S1 and S2. So, lifetime for this internal conversions, radiative emissions can compete effectively with non-radioactive transitions. So, this is radiative transitions within this, and this between this is our non-radiative transitions. So, as you can see, you have fluorescence when this red color stops happens, and your phosphorescence when this internal crossing happens to another triplet states, basically electronic spin flip happens, and then transition to the ground state leads to phosphorescence. So, these are non-radiative triplets, okay, and of this time scale given here, and okay, I can always discuss in terms of this. Please look at this part. You have excitations of the order of 10 to the minus second, 15 seconds, internal conversion and vibration reaction into the 14 to 11 seconds. Then you can have fluorescence which are this 10 to the minus 9 or less, 9 and more actually, not less, 10 to the minus 7, or you can have actually internal crossings and non-irradiative. What I have not discussed here is the quenching, which I will do it in later part. So, that is actually internal conversion versus fluorescence emissions. Again, to show you how the mirror image principle can be applied, as you can see here, the mirror image rule typically applies when there is a S0 to S1 transitions taking place. This is the excitations and this is the emission, absorption and emissions, similarly here also. So, deviation from the mirror image rule can also be observed, very rarely observed actually, when S0 to S2 or a transition even higher excited states takes place. This is one such shown here, there is deviation, but normally we see this kind of pictures most of the cases. Well, then let me just discuss more about inter-system crossing, which is the main reason for phosphorescence. Inter-system crossing actually refers to non-radiative transitions between the states of different multiplicity. As you see here, basically for phosphorescence you need to have a triplet states. So, this is what is required, and that requires inter-system crossing. What is that? It occurs actually via inversion of the spin of the excited electrons, resulting in two unpaired electrons with the same spin orientations, and this basically leads to states with a spin equal to 1 and multiplicity equal to 3. That is what you see there, multiplicity of 3, 1, 2, 3. Transition between the states of different multiplicities are formally forbidden, these are not at all allowed, and spin orbit and the vibrational coupling mechanism decrease the pure characteristics of the initial states and final states, therefore making the intersystem crossing more probable. Now, what I mean to say is that T to S0 transition is always forbidden and T1 lifetime significantly larger than this. So, if I have S0, S1 and T1, T1 is a triplet states. First, if system is excited by absorptions, okay, and then it can have IC, this is not intersystem crossing, this is internal conversion here, and then fluorescence. And if you have intersystem crossing, it leads to T1 states from this to this, and then you can have phosphorescence when it transitions happens to the S0. So, that is what is called intersystem crossing, and these are the parameters which are followed there. Again, if I put all the things together, now I know what is intersystem crossing, everything, that is what will be coming into picture. I think this is what I have already discussed, forget about this. These are all different states and how fluorescence and phosphorescence can take place. Well, let us see the spectrum. So, if I have intensity versus wavelengths, if I have two molecules, suppose here 1 and 2, and then the molecule 1 absorbs, and then if it is donates or it is just donates, then you have this kind of phosphorus fluorescence. If it accepts the molecular 2, you have this kind of fluorescence. So, non-additive test by a quantum mechanical process of resonance between the transition dipoles, normally effective distance between 10 to 100 Armstrong, emission and the excited spectrum must significantly overlap and do not transfer non-additively to the acceptors. Well, now that we know a lot of things, I will also discuss in some of the deactivation process, which actually I have told, and just show you radiation luminescence process, fluorescence, phosphorescence, which compete with each other. Relaxation, radiation less process, you can have vibration relaxation, internal conversion, external conversion, and have intersystem crossing. Intersystem crossing is already discussed. What is vibration relaxations? A molecule can give up some of this energy from the absorbed light by jumping to low energy states, and excess energy used as a conversions, no light is given off. This is what is called vibration relaxation. Internal conversion I have already discussed. So, basically to tell you that in molecular transition to a lower energy electronic state without even giving light, here also excess energy is to convert the molecule from one electronic state to another states. What is external conversion? That is what is the new thing which I am going to discuss, and that is known as quenching. Molecule give up energy to an external source such as collision, but with another similar molecule or solid molecule. That is what is called quenching. That means it can give energy to another molecule. Intersystem crossing I have already told how a single state to triplet state transitions can happen and can be used for phosphorescence. Well, vibration relaxations, normally excited state molecules collide with solvent molecules can happen. The emission lines will be red shifted, longer lambdas and lower frequencies. Lifetime of vibrational excited molecule is 10 to the minus 12 second or less. Okay, then you have internal conversion. Internal conversion basically two molecular energy levels are sufficiently closer. So, you can have S2 S1, T0 to T0, S1 to S0 conversion is called internal conversions. External conversion is basically when the energy transferred to another molecule, and which is called quenching. Intersystem is like S1 is T1, excited states flip. Well, now let me go to the next thing after talking about all kinds of principles, that is called quantum yield. Quantum yield is what is measured actually quantity. Quantum efficiency is known as the ratio of total emitted light to total absorbed light. So, when I put certain energy into system, energy is absorbed, and then when I get certain emitted light, I get back. So, this ratio is known as the quantum efficiency. So, number of emitted photons divided by number of absorbed photons, what is known as quantum emitted frequency. It can be expressed in terms of rate constants, like this one is written like this, k by k plus k n r. KNR is basically K vibration, K interchange, K escape and K interstates, and phi normally varies from 0 to 1, because there is an efficiency that has to be between 0 to 1. Well, after knowing that, let us now look at the characteristic fluorescence spectra. Universal property of any fluorescent molecule in solution is loss of energy between the excitation and emission states, and then that can be measured. So, intensity can be measured. It can be plotted in terms of quantum efficiency also, versus wavelength or intensity versus wavelength. So, you could see this is the absorption and this is the emission, they are mirror, but there is a shift because of energy law. This is known as Stokes shifts, and this lambda is very important because this is what is the emission lambda. Emission arising from the excitation of its fixed wavelengths, that is what is called XM max, is, and fluorescence emission intensity is XCM max or this. So, these are all measured, these maximum intensity peaks, both the cases, and used for the real study. So, obviously there are two kinds of spectra, one is excitation spectra, other one is emission spectra. Excitation spectra is measures the fluorescence at a single wavelength, while excitation wavelength is varied, scanned. So, you can vary the excitation wavelengths and measure the fluorescence. It is very similar to typical UV visible spectra, you know that we just scan the wavelengths of the radiations and measure what is coming out as excitation. Emission measuring the fluorescence spectrum at a multiple wavelengths, while the excitation wavelength is constant. So, you put this excitation wavelength to be constant and then measure the emission spectra or fluorescence spectra at different wavelengths. And excitation wavelength is always chosen usually at the wavelength of maximum absorption, that is the lambda max, that is what we showed you. At this wavelength, greatest number of molecules will be absorbed, that means it has a very high epsilon as per Beer-Lambert law. And to give you some characteristic pictures, the relative efficiencies of the different wavelengths of incident light to excite a fluorescent material is obviously determined by the excitation spectrum, and that is why you need to know this. In this case, excitation is monochromator, excitation monochromator is varied, that is the wavelength varies, while emission wavelength is kept constant if the monochromator is utilized. And there will be, this is what is the one, this is the another one. So, as you can see, there is overlap between the absorption and the corrected absorption. This is the corrected absorption spectrum for chemical in ethanol, and these are all plots to be made. So, plot of emission against wavelength for a given systems is known as emission spectrum, and if the wavelength of the exciting light exchange the emission from the sample is plotted against the wavelength of the exciting light is known as excitation spectrum, and the intensity of the exciting light is kept constant as the wavelength is changed. The plot of emission against the excitation wavelength is always known as corrected excitation spectrum. Okay, so now I am going to talk about how we actually calculate the fluorescent intensity and what are the factors it depends on. Normally it depends, or it is to be written like this way: fluorescent intensity is given by this formula K into concentration of the molecule present in the substance. So, that means intensity gives us certain way to measure the concentration, provided we know the constant K. K is a constant that takes into account molar absorbivities, that is epsilon, which we have discussed for Beer-Lambert's law, quantum yield, which I have just told you, sample thickness, and the light penetrating power. So, I have already discussed about quantum yield, we have discussed about molar absorptivity in case of UV visible spectroscopy, sample thickness anyways can be measured, what is light penetrating power, which we will just discuss after some time. So, fluorescence intensity actually depends heavily on the solvent properties as much as the solute, and the wavelengths used to excite the molecules obviously will also be affecting the fluorescence intensity. So, much more dependent than UV visible on variables such as temperature, etc. Temperature I have already told how it can be affecting that. Now, if we want to modify the Beer's law, it is not actually Beer's law in these cases, how it will look like. So, fluorescent intensity is given by K P0 epsilon B C phi, and K is again another small constant which depends on the solvent type, and this you can clearly see that quantum efficiency is very important factor, the concentration, quantum efficiency is this and epsilon. So, when these instrument parameters and the cell path lengths are held constants, you can write down the equation is equal to F is equal to K into C, where A is log P and K is the new constant for the system. The last equation states that intensity of the fluorescence is directly proportional to concentration when the concentration level is too low. That means when P is epsilon, BC can be Br prime by law can be applied. Now, there are factors which can affect the quantum yield. So, therefore, quantum yield must be discussed. So, what is quantum yield I have already discussed to you. So, what are the factors? The quantum yield or quantum efficiency of fluorescence process is simply ratio of the number of molecules that flows to total number of molecules used for excitations. Then you have a temperature and solvent effect. Then you have structure of the molecule affecting the structural rigidity, effect of substitutions, and you have quenching, which will come to picture. So, what are the temperature and the solvent effects? Higher the temperature, usually the lower will be fluorescence intensity, as the molecule have a greater kinetic energy and move more, a greater number of collisions can lead to non-radiative relaxations, that is called external conversions. So, that means energy will be lost more, so there will be fluorescence yield will be less. Heavier the molecule, so that is the temperature effect. Now, heavier the molecule weight solvent has, lower is the fluorescence yield. So, orbital spin interaction between the solute and the solvent increase actually the rate of triplet transitions, and therefore result in increased phosphorescence and reduced fluorescence. This is mainly because of this orbital spin interactions. Then solvent can also affect in terms of viscosity. Fluorescence increases as the viscosity increases because energy loss by the molecular collision decreases. Viscous means less energy loss. Solvent can also affect in terms of polarity, the polar solvents enhance the fluorescence. pH can affect also, pH can alter the structure of the molecule and affect the quantum efficiency. Dissolved oxygens can actually quench the fluorescence process due to crossing, increased rates of intersystem crossing and possibly oxidation of the molecule of the solute. This is normally can be totally checked. You can always check the dissolved oxygen constant, removed it also, but you cannot really fully remove it. Now, how the structure affects? The vast majority of the molecule that undergoes this fluorescence have backbones of functional groups made up of aromatic rings. This is what is you must remember. Or fused aromatic ring structure or conjugated double bonded structure. So, three things are required. One, aromatic ring or fused aromatic ring structure, all conjugated double bond structure. Benzene, which is the best molecule showing the aromatic rings, or benzene based structure, polyaromatic hydrocarbons, heterocyclic polyaromatic hydrocarbons are used, and they always show this kind of transition from pi orbital state to pi anti-orbital states. Most intense fluorescence occurs when low energy transitions in the orbital. Now, to show you how we can actually use the absorption maxima for the conjugation study. Wavelength value of the absorption maxima and the molar absorbability are determined by the degree of conjugations of the pi bonds. I guess you have all of you have the idea of pi bonds and how the conjugations can happen. As you know, you can see here that if I show it for n equal to 3 to n equal to 5, the pi bond increases from 3 to 5, and obviously pi electrons are increasing from 6 to 10, and that is how you can see the molar absorbability peaks, wavelengths are changing. So, you can see here these are for the 5 electrons, this is for 4 and this is for 3 pi electrons. So, these are the molar absorbability values 50,000, 100,000 for these molecules. So, as you can, and this is the kind of pi electron presence, as you change the pi electrons or conjugations, the absorption maxima comes at different wavelengths. That is very widely used. Now, if I go from smaller aromatic rings to larger number of aromatic rings, from benzene to the pentacene, this is way it can change. So, this is log excitation coefficient versus wavelengths. So, you can see the absorption maxima is changing from benzene 262 nanometers to 580 nanometers for pentacenes, and these are the values of the log of extinction or log of epsilon it increases from benzene to the pentachene. This is available from our results. So, as the degree of conjugation increases, the number of electrons involved in relocation pi orbital also increases, absorption energy increases, energy between the concentration and the state increases, and absorption becomes more intense. So, there will be more value of epsilon, and that leads to increased probability of the epsilon. That is the reason for such a kind of things. To talk about more about structures, vast majority of molecule, as I said, has this kind of structure and transition can happen. Most importantly, increased structural rigidity, that is benzene to base structures, and the presence of heterocyclic rings can also lead to increased fluorescence. Lack of rigidity in a molecule probably causes an enhanced internal conversion rate and a consequent increase in radiation less or deactivation substance, which is still not accepted widely, but normally this is what is believed in the literature. Well, before I discuss the instrumentation, let me just talk about definition of quenching. What is it? And fluorescence quenching is widely used. It basically leads to decrease in the quantum yield. Efficiency of conversion of absorbed radiation to fluorescent radiation is extensively decreased because of quenching. And what are quenchers? Quenching is nothing but reduction of the fluorescent intensity by presence of certain substance in the solute sample or in the solvent actually, other than the fluorescence analyte. So, as I said, certain amount of energy is transferred from the fluorescent material to the solvent, and you can have different kind of quenches, inner filter quenches, filter quench effect, that is absorption of incident or emitted radiations because of quench substance, or you can have dynamic collision quenches, which can reduce the fluorescence by dissipating the absorbed energy as a heat due to collisions with the quenching species. Quinine is basically a fluorescence, highly fluorescent in 0.05 m molar H2SO4, but non-fluorescence in 0.1 HCl due to collision quenching of the chloride ions. Chloride ions actually absorb the energy by as a heat. You can also have state quenches, like we can form a chemical complex with fluorescent substance and alter its fluorescent characteristic, like caffeine, a xanthine derivative reduced the fluorescence of riboflavin by static quenching. So, caffeine can absorb or form a complex and absorb the fluorescence molecules. A color species in the solution with a fluorescent species can interfere by absorbing the fluorescent radiations, that is what I discussed. Potassium dichromate exhibits absorption peak about 245 and 348 nanometers. This can overlap with excitation emission of peaks of tryptophan and would therefore interfere. That is also can lead to quenching. Inner filter effect can actually lead to too high concentration of the fluorescence itself. So, to show you how, so first you see that the increases, and then because of cell absorption the fluorescence decreases. So, therefore, nonlinear calibration curves gives a high concentration of the analyte due to interflow effect can cause negative curvature in the calibration curve. So, we must consider this while calibrating this. Well, now what kind of molecules, as I said already, can show this. So, as you see, benzene or anthracene or the benzopyrene, they are the aromatic ring molecules, or a amine alcohol group, methyl oxymethyl group, or some other groups can also give you. And one can choose careful pH. pH gives to affects the corrosion, the quantum yield and the fluorescence yield also. Aniline is cationic at acidic pH, do not fluoresce, but in pH range of 7 to 12 it can actually act as a neutral species and fluoresce. So, you can see this positive ion or positive species here leads to mix in non-fluorescence. Dissolve of oxygen and impurities, as I told earlier also, can quench and results in less fluorescence. Last thing which I am going to discuss is basically the instrumentations. So, what you need in a photoluminescence spectroscopy is a light source, monochromatic systems, samples or cell compartments, emission monochromator and detector systems. These are the 5 things you need for this. So, comparison of the flow meter actually, what is the heart of this machine? It contains 2 monochromators, one before and one after the sample, one absorption, one on fluorescence, whereas spectrophotometer has only one may be located wherever you want, and in spectrophotometer the transmitted power is always measured, that is the detector actually is always transmitted power is always measured by detector which is parallel to the path of the incoming beam in the fluorescence. In the other hand, it is necessary to measure the property of fluorescent emissions, not the transmissions, by a detector which is right angle to the path of the incident beam. And there are different properties of the fluorometer. Fluorometer has to have single wavelengths, it has filter based instruments, it must be having wide bandwidth, and filters are chosen for specific analytic, and we do not use any reference also. So, to give you in a nutshell the whole picture, you have a light source for excitations, then this is the excitation monochromator, then you have a slit through which this monochromatic radiation passes through, falls on a cuvette sample in a cuvette, and then unabsorbed excited lights comes out this way, which can be detected or not detected, and whatever fluoresces it passes through a slit, and then you have emission monochromator, and which allows these emitted rays to be detected in a fluorescent detector. This is what is the schematic diagram for the right angle geometry fluorometer. Many of these lab has this. Spectrometer, which is a scanning fluorometer actually, it can spectrofluorometer can scan the wavelengths, it has a very high quality optics. Two monochromators as I said we used, one is for the excitation, one is for emissions, it can hold 1 centimeter cells or samples, and there can have 4 optical windows, can do all kinds of scans mean wavelength scan, other scans, can measure the fluorescence and the chemiluminescence, usually do not have separate different cell holders, background can be collected and subtracted. What kind of radiations we use? Unlike absorption sources, you have necessary to have fluorescent sources. So, normally the two most important sources are used as mercury arc and Zener arc lamps, and there has to be maximum sensitivity. So, mercury lamps sharp line energies, Zener lamps provide relatively smooth spectrum, very large, this is 2000 to 8000 Armstrong, and for fluorometer UV visible spectroscopy you have mercury lamps, Zener lamps both, you have tungsten as I ever discussed for visible, and deuterium is used for UV. So, as compared to this, these are all used in the fluorometer. You can always have a monochromator, and monochromator actually makes the light of single wavelengths, it disperses the radiation, isolate the desired wavelengths, it serves as same as a function of monochromatic system in spectrophotometer. You can always use a filter between the light path and the sample to get a certain kind of wavelengths, and I have discussed in detail about monochromator at certain kinds. Samples are contained in cells, and they are inserted in a dark baffle systems. This absorbs stray light, and majority of the excited lights from the sample and the cell is comes and then detected. You can have 1 centimeter cells, or you can have 4 optical windows instead of 2. Detector is basically nothing but a photomultiplier tubes. It can scale up the radiation which is coming out. So, intensity of light will strike the samples P0. Alternatively, sensitivity of detector can be changed by various sensitivity controls, most notably photomultiplier tubes are capable of doing that. And the different fluorescent substance, as I said, quinine, anthracene, rhodamine, and PPO or PPOP. This is taken from the books of the Thomson. Well, finally, what are the applications? Fluorometry is generally used if there is no calorimetric method, sufficiently sensitivity or selectivity for the substance. So, analysis of metals. Most frequent applications are determination of metal ions as fluorescent organic complex, like aluminum forms fluorescent complex with aerochrome black blue. Analysis of non-metallic also, like anionic bases can be measured, like condensation reaction between boric and benzoin. Organic, I have shown a lot of examples. Some of the important organic applications are quinine, riboflavin, and thiamines. So, with this I close this discussion on the photoluminescence spectroscopy. Next class I will discuss about Raman spectroscopy.